event, and today we have Professor David Dunson from Duke University. He received his BS in Mathematics in 1994 from Penn State and went on to getting his PhD from Emory University in 1997 in biostatistics. And he works, his research interests are very extensive. Bayes is the main focus, but there's also big data, epidemiology because of the biostatistics training, and then machine learning, non-parametrics, Bayes, everything. And there are lots of very interesting things in his resume, especially the things that caught my attention are some of the publications. He has a tremendous list of publications, and he has actually categorized them according to journals. Okay, you want to listen? JASA, 35 or so, because I lost count after a while. Biometrica, 22 or so. JRSSB, 6 or so. Annals of Statistics, 6 or so. Biometrics, 37 or so. Other statistics journals, I started counting 70 or 80 or 90, and I said, no, I'm not too good at counting. But extensive list of publications and variety of topics. And similarly with grants, he has several grants from all possible sources that you can imagine. But he in fact spent the first 11 years or so, 1997 to 2008, in biostatistics branch in National Institute of Environmental Health Sciences. And then he got into Duke University as a professor directly in year 2008. Of course, he moved up in rank in NIEHS, I guess. And then he's now the Arts and Sciences Distinguished Professor from May to 2013. And of course, he's received several awards. David Beyer Young Investigator Award in 2000, Fellow of the American Statistical Association in 2007, Mortimer Spiegelman Award in 2007, Fellow of IMS in 2010, Fellow of International Society for Bayesian Analysis, and so on and so forth. And he has won a lot of awards for various challenges, data challenges, graph challenges, and then of course he's won the prestigious COPS Award in 2010, the COPS Award in 2010. Editorships, of course, he's the current editor of JRSSB, and he's been an associate editor for Biometrica, JASA, and many other journals. And when we contacted him, he agreed to give a talk, and he actually wrote a very nice note to Abhiday. And he also copied me on that, and I think that's really worth mentioning. He wrote about some of his unique connections with UGA and Georgia in general. In fact, there's actually a Dunson native plant garden in State Botanical Garden of Georgia named after David's grandfather. There's also an amazing history of connections of his family to UGA. Okay, what are those? Apparently, a Dunson donated the logs for the first cabin that was the start of UGA in the early 1980s. Not 1800s. Grandfather is a very young grandfather. 1800s. Both his grandparents received BS and MS degrees from UGA, with his grandmother the first woman admitted into chemistry and the first woman to receive a degree in chemistry. He still has relatives living in this area. Professor Dan.
Thanks a lot for the kind introduction. It's a big honor, and so I'll just proceed. Yeah. So I'm going to talk about today about the title was on modeling of big tables and networks. And so basically the deal is as follows. I think a lot of people are aware that there's an enormous emphasis in modern literature on high-dimensional data, and so you have very high-dimensional data, but I found that there's been very little focus on high-dimensional discrete data. Most of the focus has been high-dimensional continuous data, things like high-dimensional regression, covariance matrix estimation, etc. But I found in my collaborations that there was a ton of data that are high-dimensional discrete data, and there was really a lack of methods to deal with these types of data. So say we have, this is like an old school chalkboard, we have some sort of vector yi, okay, and so we have yi1 to yip. So this is, say, subject I, subject, and then each of these guys is, I'll be assuming, is categorical, say 1 to dj. Okay? And the initial motivation we had is actually modeling of nucleotide sequences. And so we have A, C, G, T, and we had a genomics type application where we were looking for what are called transcription factor binding sites or gene regulatory sites within a long DNA sequence. And there was a set of models that just assumed that the ACGT, the sequence, was independent. Okay? And they would proceed under that assumption, searching for these transcription factor binding sites. And the computational biologist, whose name is Zing, he came to me and said, you know, I really think there should be some sort of dependence across that we should put in the model, and that might help us find better transcription factor binding sites. Okay, and so I started thinking about it, and it was amazing how little literature there was. So you can imagine, okay, well, in animal or organism I, you might have a sequence at different locations, J, and they might be, in this case, it would be 1 to 4. Okay, so it would be A, C, 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 G, whatever. Okay? And so that's your data, and you'd like to allow for dependence in that. Okay? So how do we kind of do that? Well, we could imagine this is just multivariate categorical data, and so then we have some sort of joint probability for these multivariate categorical data. This is a really uneven chalkboard. CP. Okay, so that would be at position 1, you have nucleotide level C1, ... up to position P, you have nucleotide level CP. Okay, so that's some joint probability mass function, and we could say, well, that's pi sub C1 through CP. Okay? And so you could imagine that this is sort of a table of probabilities. So if we only had 2, if P was 2, we're going to have this kind of deal. Okay, and then each of these cell probabilities is this pi guy, and there's going to be a lot of probabilities as the dimension of the table increases. So even if you have a 2 by 2 table, we're going to have 4 squared 16 cell probabilities here. And in general, the number of cell probabilities is going to be like the product from j equals 1 to p of dj, where dj is the number of levels of this categorical variable, and so if it's a nucleotide sequence, it would be 4 to the p, which is blowing up really, really fast in p, amazingly fast. And so we're going to get lots of parameters in this table, okay? And so if it's a 2 by 2 table, it's a matrix, but we can imagine that it's going to be, even if we go to 3 dimensions, we're going to get sort of a Rubik's Cube or something, and so that'll be what's known as a tensor. Okay? And so if you have a 2 by 2, it's a matrix, and a higher order extension of a matrix is a tensor. And so this whole thing, this kind of cube or hypercube of probabilities, we could think of as a probability tensor. Okay? And so we could say, well, this pi is a p-way probability tensor, and the elements are these cell probabilities, C1 to CP. Okay? And we're interested in characterizing the joint distribution. And so you've probably all seen a lot of methods for characterizing the joint distribution of continuous variables. The usual thing would be maybe a multivariate Gaussian distribution. And we have a p-way Gaussian, and then we would have a big covariance matrix, sigma, which would be p by p, and we might want to estimate the covariance, or we might want to do inferences on the associations among the variables based on the covariance, or perhaps the inverse covariance. But here we instead have all these cell probabilities, and so the one question is, what do we do with that? Okay, so how do we estimate these cell probabilities, and how do we do inferences? And so before I talk about that, I'm going to talk about two motivating applications. The original motivation that started me working in this line of research, which started in the kind of mid-late 2000s, was the nucleotide sequence. But there's really a much broader set of applications. And so we could say application one is kind of surveys or social science surveys, or you can imagine that, okay, well, I get a sample of people and I ask them a bunch of questions. So what's your ethnicity? What's your gender? What's your religious view? What's your view on different political topics, on different stances? And so you might ask a whole bunch of different survey questions. And so, in the one, we were looking at the public use micro sample of the American Community Survey, and in that setting we had P was equal to 40, you know, and then N might be, it was approximately, for the set of data that we were looking at, 35,000. Okay. And you have lots of people answering lots of different questions, and so now we want to know what the association is. You know, what's the association between, you know, your ethnicity and your religious views and your political views on different topics. You might want to predict how somebody views abortion or something based on their other characteristics. Okay, so we like to do things like that. But if we think about it in this case, the table, you know, maybe each one of them might be 4 or 5 levels in general in these types of things. You have this like Likert scale thing. And so the table is something like 4 to the 40 elements in it if you're looking at just kind of estimating all of these cell probabilities. And so that's a lot of parameters. It's probably more parameters than there are atoms in the universe. It's a lot of parameters. Maybe not quite that much, actually. But as you make P bigger, it rapidly gets to that level. Okay, and so we have a lot of parameters. So that's a problem. And so the second application that I'll be using as motivation is actually brain connectomics. Which has a little bit different flavor, but the data are kind of similar, actually. And so I've been working on this a lot lately. It's kind of really fun, find it anyway. So this is somebody's brain, and this is the right hemisphere and the left hemisphere. And we could imagine breaking the brain up into regions, you know. And also, what people can do now is they have these wonderful MRI machines where we can get pretty accurate, I think, hopefully accurate, somewhat accurate, estimates of the structural connections in your brain. So your brain is broken up into gray matter and white matter tracts. The white matter tracts have like tightly bundled neurons that are spatially aligned in so-called fiber tracts in the brain. Okay, and so there's going to be a lot of these kind of fiber tracts. And on the next slide, I'll show you a picture. No, so there's all these fiber tracts in the brain that are spatially aligned, and they act as highways for neural activity. And so the neurons are connecting different brain regions, and there's a lot of processing going on when you're doing anything with your brain, moving around your body, or processing visual stimuli. And we're really interested in, well, what aspects of this brain connection structure are related to phenotypes or traits of an individual? So it could be your creativity, your IQ, or depression, or anxiety, or right now we're putting in a big grant on autism. And so we'd like to figure out how that structure is related. And so what do people usually do? So we have like 1 million fibers in the brain. Usually people kind of pre-process that and they turn it into a matrix. Okay? And so this is R, say R by R. R is the number of brain regions in our segmentation. Okay, so here we like 2 brain regions. Here's a brain region. Here's a brain region. There's going to be a bunch of fiber curves connecting those brain regions. We can count the number of curves connecting the brain regions, the number of white matter tracts, and that's going to be one cell in the table, and that'll be a number. Okay? Almost always what people do is they then threshold that, and then that turns into 0, 1 indicator, and so we get this matrix of 0, 1 indicators where the connections are. Oh, this corresponds to a particular individual, whether there's a connection in that pair of brain regions. Okay? And so you can see, that's what people usually do. And so that looks a lot like this. Okay? So we have individual I, we have p pairs of brain regions, which if you have r brain regions, that would be r times r minus 1 over 2 would be p. Okay? And so, and each one of these, this would be, yi1 would be a 0-1 indicator of whether there's a connection between the first pair of brain regions. We have some arbitrary ordering, and we can kind of stack it up like that, and we have multivariate binary data. Okay? But we might have a network type structure. And so these are two kind of motivating applications that I'd like to kind of develop some class of methodology that can attack each of these applications and many other applications as well. Okay. Are there any questions about that? No? Okay. Okay, so what do? So really the big problem we have is dimensionality. And it's a lot worse than some of the so-called large p small n problems where you have the data dimension is p and the sample size is n. And so sometimes p is like way too big relative to n, and that's a problem. So here, you can think of p as being the number of cells in this table, and then the sample size is the number of replicas we have here. Okay? And so clearly, d to the p is huge, and the sample size we might get in a given study, say one of these brain connectome studies, it's going to be unlikely that we're going to have more than, say, 1,000 individuals in our study that we gave brain scans to. And then if we put it in this table, then we have like 100 billion cells in the table. We're going to have more than that. Then almost all of the cells are going to be empty. We're not going to have anybody that lives in a particular cell that has a particular combination of brain connections. Yeah? And so that we have this kind of ultra sparsity. Maybe we can be helped by some low dimensionality in the data. For example, the brain connectomic data, I was quite surprised because I thought the data would be really noisy, but almost all of the structures share across individuals. And so these binary matrices are very, very similar across different people. So maybe we can exploit that. Okay, so what can we do to address this dimensionality problem? We need something to reduce dimensionality. I usually kind of model that. Well, if I had one of these variables and I was having the others as predictors, I might use logistic regression. But if I have a whole bunch of categorical variables, then the canonical thing to do is a log linear model. So I would take this probability mass function, I'd apply some log, and I'd sort of transform it, and then I would expand it out in terms of, say, two-way interactions between different variables, and three-way interactions, and four-way interactions, etc. Okay? So that's a typical thing to do. And so if I set a lot of those interactions to 0, then you could call that a sparse log linear model. Like a sparse model, you're setting stuff to 0 usually. And so idea one is, well, I could use some sort of sparse log linear model. Log linear. Okay? And there's, of course, a literature on that. Not very big, surprisingly. Like, I was amazed how little people have addressed this type of problem in the kind of modern era of high-dimensional statistics. And so, but there is a lasso or an L1 penalized log linear model method where you could try to fit the log linear model and put some sort of L1 penalty on the coefficients, which is going to favor lots of the estimated coefficients being 0. We found two big problems with that. The one is if you simulated a true sparse log linear model, and then you fit this lasso log linear model approach, it did incredibly badly. Even in quite low dimensions. P could be like 10 or something, and n could be pretty big. The lasso log linear model method didn't really work for our purposes. Okay? The second problem is that the current methods using log linear models are graphical log linear models or log linear models with a Bayesian approach where you're trying to shrink or something. They don't scale up very well because if you think about the number of coefficients in the saturated log linear model, which had all possible interactions, that's just too big. You can't even store it on your computer. And so you can't possibly be searching around trying to do computation in this log linear model with too many terms. You might want to do something like rule out everything beyond two-way interactions, but that doesn't make a lot of sense. I was talking to Andrew Gelman about that, and he likes this concept of deep interactions in his social science applications he works on a lot. And it often makes sense that there's three-way interactions or four-way interactions. They might be small, and so we don't want to rule them out a priori. Okay? So we didn't quite want to do that. We kind of liked it for interpretability, but it wasn't practical. The computability aspect and the accuracy are not good. So idea 2 was an idea that I think in this context was somewhat original to us, but there was a previous literature that was motivated by other contexts. Is to do some sort of low rank. Okay, so I want to reduce the dimensionality. Maybe I can do some low rank factorization. Okay, and so I could think, well, this guy, these are the cell probabilities in the big table or tensor, and so maybe I could take that tensor and write it out in a low rank expansion. Okay, and so if it was a matrix, then there's a huge literature on low rank matrix factorization. That's going to reduce the number of parameters. And so I could maybe extend that low-rank matrix factorization to a low-rank tensor factorization to reduce the number of parameters. Okay? And so let's play with that. Well, you know, the typical class of tensor factorization, the most common class is known as a parafact, or parallel factor analysis factorization. And so we could take this tensor pi, which is a p-way array or tensor of cell probabilities, and we could write it out as like in this kind of low-rank form. And I should say for tensors, for matrices there's one unique definition of rank. For tensors that's not true. So it's more complicated to do factorizations of tensors. But, you know, we could use this type of factorization, say. Okay, so what's this? So this would be, if I have a tensor pi, and usually it wouldn't be constrained to be a probability tensor in the literature, but let's say we have this tensor pi, we're going to write it as a sum of k pieces. And if k would be the rank in this parafact sense of rank, if this is the smallest case such that we can write it in this way, where these guys are each vectors. And so we're writing it as an outer product of vectors, one vector for each element in the factorization, and one vector for each dimension. Okay. And so that would seem promising. In the categorical data case, we could actually maybe write it as follows. It'd be equivalent, but maybe we can say, oh, pi h lambda h1 lambda hp, okay? Where this guy is just a scalar on the probability simplex, and so these pi h's are going to be between 0 and 1 and sum to 1, which give us a weight on the importance of component h in the factorization, okay? And then these guys are just probability vectors, and so if this one would correspond to our first categorical variable, and it would just be equal in dimension to the number of levels of that categorical variable. So it would be d1 probability vector, and this would be a dp dimensional probability vector. And so if it was a nucleotide sequence, and so they were all 4-level, this would be a 4-level probability vector, and this would be a 4-level probability vector. Okay, that make sense? And so the one nice thing about this is by making these all probability vectors, we're constraining this pi to be a probability tensor, and so which would then be appropriate for modeling this kind of joint distribution of multivariate categorical data, which is cool. Yeah, and so it also has a dual interpretation as a mixture model, and so we could say that, we could think that the data are generated, you know, given some zi from just independently from multinomial 1 to dj. We're generating the jth categorical variable in subject I, given this latent class index or subpopulation index from a multinomial, and the multinomial probabilities are just going to be for this jth variable are just going to be that, and then the probability that zi is equal to h is equal to pi h. Okay. So to generate data from our tensor factorization, or probabilistic tensor factorization, we could generate for each individual a subpopulation index Zi, which is just categorical from 1 to k. The probability of being allocated to component h is pi h. Once we have the Zi filled in, we just generate from a multinomial using the probability vector relevant to that particular categorical variable and relevant to that particular latent class. Okay, and so it becomes very easy to do the computation. Okay? Very easy, even if it's pretty big. In fact, we can just, if we take a Bayesian approach, we could do it for the non-Bayesian approach, but if we take a Bayesian approach, then all we have to do is we need to put priors on the probability weights in each of these vectors. We just put Dirichlet's on all of them, okay? And then we can just do a super simple sampling algorithm. What do? Okay, well we initialize guesses of the parameters for each of these parameters, okay? We sample each of the ZIHs from their conditional posterior distribution, which is just going to be multinomial. Okay, it's going to be very simple multinomial. It'll be, the probability that subject I gets allocated to component H is pi h, the prior probability, times the likelihood of the multivariate categorical data given that component index. That's going to depend on the pi's, and then we just normalize. So then we fill in all the Zi's. Once we filled in all the Zi's, we just have conjugate Dirichlet sampling of the pi's and each of the lambdas, and it becomes, so it's super simple. Okay. And this idea was published in a paper, some people call it DX paper, 2009 in JASA. Okay. Jerry Ryder's used it really successfully a lot for imputing missing data in multivariate categorical data analysis, or generating synthetic data sets that mimic some sort of data set that's confidential and you can't release. Okay. So this works pretty well, and it addresses the dimensionality problem somewhat. And so the original problem was, okay, the number of parameters is sort of like the order of, like, just say all the d's are the same, like d to the p. Okay, well, this reduces it down to be linear in p. Okay, because we have, like, if we have fixed k or rank, then we're just having the number of parameters increasing linearly. We have a vector of a fixed dimension for each dimension, and then we have these k, and so it just increases linearly. So that's a huge dimension reduction. And we found this type of approach works quite well if you have maybe 30, 40 variables, something like that, dimensions. It works really quite well. And it's been pretty, used quite a bit successfully. Okay. But the question we have is, like, okay, well, now if we do just low rank, it increases linearly. And P, okay. Well, if P is very big, that's still going to be a problem. It's not low dimensional enough, And so we'd like to put in, or need to put in, some additional degree of dimensionality reduction if we're going to be relevant in the brain connectomics application and other or for longer sequences, where we're not just focusing on a little bit of sequential data, or if we have data like single nucleotide polymorphisms or something like that in genomics. And so we need to do something to make it more dimension reduction. And what we were thinking about is in that respect is it's useful, I think, sometimes to kind of step back from the modeling and think a little bit theoretically, and I can sort of just put the concept up here that we'll get back to, and we can say, okay, well, here's the set. Let's say that pi naught, this is the true probability that generated the data. And so if we have this joint probability distribution on these p categorical variables, we don't know what that is, and so if we take a Bayesian approach, we put a prior on that probability, and then we update with the likelihood, and then we get a posterior distribution, and we do inferences based on that. But we can think in sort of a frequentist hypothetical way and say, oh, well, let's say there's some true probability pi naught, okay? And that lives somewhere in this space F or something, okay? We don't know what that is. This is a true joint probability. And this F is the set of all probability tensors, all p-way probability tensors. So they're all joint probabilities that could have generated these p-dimensional categorical data. Okay? And so one thing that would be nice is for our Bayesian approach to have some property like, okay, well, let's say we put a little neighborhood around the true probability. This is an epsilon neighborhood. Okay? So epsilon, arbitrary small number. We put some little neighborhood around that true probability. What would we like our posterior to do? Anyone? So we have a posterior. Now, here's our pi. This is like, well, in a Bayesian approach, a frequentist approach, you get a point estimate pi hat. You know? You might want your pi hat to converge to pi naught as the sample size got bigger, hopefully fast. So in a Bayesian case, we have, well, pi is like a random variable. And so we have a probability distribution, which is the posterior distribution, which is allowing for uncertainty in pi. The Desicon, this paper, Atlas.
Your K number of components known or it's also unknown?
That's a great question. So that was a big aspect of our paper was is I really like Bayesian methods that can kind of shrink towards lower dimensional structure without restricting it. And so there's actually, you can think that there's a weight here. The weight is stochastically decreasing according to some shrinkage prior. And so if the data contains a lot, and so it'll adaptively tell you how many components, and it'll kind of shrink towards few components. And that seemed to work pretty well. It's sort of related to this paper I had with Anirban Bhattacharya in Biometrica in 2011, that type of idea. But it seems to work pretty well. And this paper is coming out in JASA Theory Methods, as they have here, invited discussion paper. And I'm going to present like the details at GSM on just that part.
So how do you decide the K in the tangent? How do you make sure that the model, the decomposition is identified?
That's a great question. Again, it's a related answer. So we're actually we're doing this kind of shrinkage, and so the pi h is actually modeled according to a stick breaking process, and so conceptually K is like an infinite. But the components, the pi's are becoming very small rapidly. And so if you simulated from something that had, say, k equal 3, it's going to figure that out and then shrink down really quickly the other components. But it'll figure it out. Instead, it should be k equals 4. Probably in reality, nothing's actually fixed finite rank. And so you want to kind of shrink towards a lower rank structure. And the stick breaking prior does that. And the over here we have a different prior to do that because we have this two unknown things. We have what's the dimension in the latent space and what's the dimension in the kind of mixture model or tensor factorization part. And so you can figure that out. In terms of the identifiability, that's also really interesting because we don't, like a lot of the approaches if I'm doing frequency optimization or something, well, how are these lambdas identified? You don't care at all because I don't care about these parameters at all. I care about pi, and I care about functionals of pi, and you can define it in different ways. We don't care at all. And so that's the cool thing is that, like, I don't want to estimate k. I define it in this way, the expansion. And so I'm putting a prior on that penalizes very high values of the pi's. Okay? And so then I get a posterior, like I'm over here, prior over here, and then I'm inducing this joint probability. The joint probability is what I care about. And so it has really wonderful behavior. Whether or not I can identify individual components, or I could identify, if I can get the rank well, or I could identify the rank in a different way, or it's invariant to certain operators or something, it doesn't really have an effect on my procedure for doing inferences on pi. It's a harder problem, and I agree we should put more constraints on or something if we wanted to actually do inferences on these different components. But often you don't care about that directly. And our Bayesian approach, we kind of get around having to care about it directly.
Any other questions? not, it's amazing that when the technology fails, the blackboard bails us out. And of
Nice to have a blackboard.
course, a speaker who knows how to write on blackboard with a great handwriting and a great topic. Thank you very much.
Going to have. Oh, I thought we were going to repeat the talk.
That would have been exciting.
Okay. All right. That was an amazing display. Okay. You see the mastery of the topic. I'm really pleased to introduce our birthday lecturer, Professor David Dunson, the 23rd birthday series of this lecture series. Professor Dunson, I really don't have much new to say because already most of it has been covered by Sri. One thing that I can tell you that I am being photographed, and when I said that you'll be photographed, and so what? I did. I ignored my prior. I became a bad Bayesian, and I brought this thing from home. And unlike Dr. Srirao, I cannot go back and put it back home. Okay. So anyway, so I just did not use my subjective prior that the Bayesians, they do not dress up. And David is no exception. David,
Gauri, David is the reason I went and kept my coat back.
I know.
I saw him, I didn't want to sit there.
But I can go back.
Good.
David has extensive research interest in Bayesian methods for complex applications, and you have seen some of these things, and you will see some more. About David, his research area is, all about solving problems, big data and complex modeling. And I was reading his 32-page Vita, and all solid, either external funding or publications. And the publications, clustered like journals. I have never seen it there. Like more than 30 papers, more than 40 in JASA. And one thing that I noticed there that his H index is 54. And since 2010 it is 43. That means what, David? If I know my story right, you are qualified to be the department head, department chair in your department. There was this background story actually about that. The dean would like to have someone with H index 40 or higher to lead the department. David, if my information is right, I think he may be the only statistician receiving both the Spiegelman Award and the Kops Award. There are not too many actually. There are not too many. And another thing is that before joining Duke, David was in this National Institute of Environmental Health Statistics, and for his exceptional research, he received a gold medal for exceptional service from EPA. David, you are lucky that you started early. There may not be any EPA. David is, as you know, he's highly active, and naturally he is in many editorial board. Right now he is one of the two joint editors of GRSS Series B, associate editor for Biometrica, JASA, Biometrics, and he has supervised many students, more than 30, and he has supervised about 30 postdocs. And I was counting that some of the names I looked at, we really badly messed up actually. You gave us actually 3 chances to hire one of your students or postdocs. And hopefully, the fourth chance we get, we'll grab it. So please send some more towards us. Anyway, I think I should allow David to present his new stuff.
Weird talk.
And,
Thank you for the great introduction. Yeah, after everyone looking through my CV, it was like, I haven't updated my CV in like 5 years. Like my website's terribly outdated. I was going to hire an undergraduate to maybe update my website. It's kind of embarrassing. Yeah, anyway, I'll hopefully keep this short. It's kind of a bizarre short talk, and so touching on artificial intelligence, data science, and brain connectomics. And I had this sort of Dunson family side thing, and so I Googled Dunson, and like I got all these kind of bizarre images, and so I just stuck some of those on there too. Okay, so here's the outline. I have this kind of Dunson UGA weird history that I'll go through briefly. Give some rambling thoughts on data science and the rise of machine learning, which I think are maybe a little interesting. Really briefly comment on deep learning, because that's a very sexy, timely thing that's really been having a very high impact, I think. Broader than statistics, but on society. Then I'll comment really briefly on real science and the impact of these types of machine learning and deep learning methods on real science, and just illustrate how maybe those methods don't do so great for real science through just a brain connectome application, which is kind of building on what I talked about earlier, and then I'll just have a summary slide. Yeah. Here's my second. You Google Dunson, it's like this like company that sells cowboy hats or something. Okay, so the Dunson history. So I guess I didn't realize this really, but you invited me to give this lecture, and so I sent it to my uncle and my dad, and so they gave me this big history. So this is my grandmother. So before that, it was a direct line descendant, like through my grandfather, from a Dunson farm, donated the logs to build the first building on the UGA campus. And my grandfather, I guess he got some funky tie. They invited him to the 150th anniversary event. And this is my grandmother, Eleanor Dunson. And so she was initially denied admission by the chemistry department chair, who really honestly thought that women's heads would explode if they studied chemistry. Yeah. And so she, for that reason, went to Louisiana State for 1 year, and then the chemistry department chair died. And she moved back to UGA in chemistry, and so she was the first woman undergrad, and then the first woman graduate student in chemistry. And I remember she was like super brilliant. She could read a book like just flip through the book, and then she remember everything in the book. She was that kind of person. She was amazingly smart. And she met my grandfather here, and the kids, they both went, the two sons, they both went to Harvard and Yale without finishing high school. Yeah. And so here's my grandfather, and so he was, maybe not quite as smart as she was, but did better in those days, day and age. She would like back him up, even though she was much more brilliant than he was. And he was also an undergrad and then a master's student in chemistry. And at the time, I guess the graduate RAs, you had to be funded by a local business. And so he went out, and there was some sort of scandal going on where they would sell ice cream, and then they would put oleomargarine in the ice cream because it was cheaper. And so his master's thesis was focused on developing an assay to detect margarine in ice cream. And so I guess he was apparently really popular in the lab because he would buy these things of ice cream, and then he would need like a tiny bit to study to do his test on. They would have this whole bin of ice cream left over, and he'd use that to attract my grandmother. But, I also noticed, like at the time, he was this very hefty guy, and like when I knew him, he was super skinny, and so he was eating all this ice cream, and he kind of bloated up. So it was kind of interesting. Later on, he went on to fund a large chemical company, actually, and they even made maybe unfortunately chemical weapons that the U.S. used, like Agent Orange. And he, I guess one of the Coca-Cola, early on, he was a businessman in Atlanta with this big chemical company. One of the guy was like going to try to launch Coca-Cola and tried to get him to invest in the company, and he turned him down, which was an incredibly stupid move. Okay, so his brother worked in the botanical gardens, and there's I guess right by here, there's a Dunson native flora garden. So that's my great uncle, named after him, who was very much into native plants and stuff. And so here's some random native plant pictures, maybe native plant pictures. I don't know anything. Anyway, so from them, like all my family are like chemists and biologists, and I was the weird black sheep mathematician and statistician. Okay, so shifting from Dunson weirdness on to data science, I think that it's been quite interesting. I think the data science revolution that's kind of taking over everywhere. Obviously, we live in the era of big data, and there's been a huge interest in how we can harness the data. And I think that, but there's been this weird thing in machine learning and data science. Like data science was originally a term coming out of industry, like in these Google-type applications. They wanted to hire somebody who could do good stuff with data. Like you'd have big, complicated data coming in. Somebody who had a stats training, they couldn't really do much because they didn't have the computing skills. They didn't have the savvy, and so you need to have like computing savvy, and then you need to know something about the application area. And then maybe you needed to know something about statistics and modeling, and combine those in a savvy way. And it was like an industry problems, And so that's kind of moved on to the next generation, and with the rise of artificial intelligence. And there's been amazing developments really on problems like automatic labeling of images. Like you take a bunch of pictures of different things, and it can tell you what's in the picture. Or many people will notice that the voice recognition software, I remember like 5-6 years ago, a little bit more than that, was terrible. And now it's pretty amazing. Recognizing patterns in images. I would say stuff like virtual assistants have gotten amazing. Like my son has this Amazon Echo thing, and he'll like talk to it and it's like tell it to play this different type of music or set an alarm for him, and it works really quite well. And that's been come really far, I think, and so that's been really kind of cool, and it's created this enormous vibe and hiring in this artificial intelligence field, like massive numbers of jobs. There's a lot of people in machine learning that they'll be sitting in academics and they'll triple their salary or even buy them out for tens of millions of dollars to go in and head groups in artificial intelligence and in industry. So that's been pretty interesting. So what is data science? Here's another funny Dunson thing. I said that already. It's this kind of art of combining these kind of different skills, and it's having a really big impact on all of our lives, I think, except for people who try to avoid devices and Facebook and everything. The search for information has gotten a lot better. Virtual assistants have gotten a ton better. There used to be this shitty like paperclip in Microsoft. It was horrible, but yeah, so it's gotten a lot better. And data science hiring has gotten a lot better. It's sort of created an influx of funding. It's raised faculty salaries, even in statistics, I think. And so what's actually behind these advances? Maybe a lot of you don't know, but I'd say one of the main set of algorithms behind it is what's called deep learning. Okay, these deep learning algorithms. And so what the hell is deep learning? Well, deep learning is it's basically a neural network model. And so the same type of model, these kind of convolutional neural networks, have been around for like a long time, like 20, 30 plus years. And then what happens is that the model is kind of sort of roughly motivated by the human brain, but it's not really a good biologic model of the human brain. And you can build it up in layers, and the models have tons of parameters, and they're really flexible and black box, okay? And so why is it taken off so much if it's been around for so long? And now people are using it, in all of these algorithms that Google uses and Facebook uses and on our devices and everything. There's been two big developments that have caused this. And the first is that there's a large amounts of labeled data. Like we can get maybe even hundreds of millions of labeled images, okay? Use things like Mechanical Turk, get tons of labeled data, like humans label tons of data. We have that, and we also have big improvements in computing resources and the ability to harness them, okay? there's actually been no improvements in the sort of statistics or the modeling that have been behind all these advances, which has been pretty depressing, actually, for a lot of us. It's all like more data and more kind of computing and algorithms for like dealing with the data. And that's not really an overstatement. I think that that's pretty true. And then you get this kind of black box predictive algorithms that are kind of fantastic in certain settings, but they require a huge amount of labeled data. That's key, yeah. And also typically the data are really highly structured, like super good at images. It's really good at like audio recordings of speech, stuff like that. It's really good at that kind of highly structured, like image, it's like spatially structured or structured in time. Okay? And so it works really well in that setting, and it's really kind of had a big impact. And so, so I'm like friends with all these machine learning people on Facebook, and I've sort of blinded a lot of them because they have a different culture than statisticians are kind of understated, and the machine learning people are like, oh, I'm giving a talk at these places, and I'm doing fantastic stuff, and like, oh, look at this great success we had in deep learning, and like getting the computer to play a game like this kind of AlphaGo thing, if people have heard about that, like play this Go game really effectively against humans. Now, why don't we solve all of humanity's problems? Like I had one of my friends on Facebook do that. Like, why don't we now solve all these medical problems and genomic problems and human health problems with these kind of amazing new deep learning algorithms that we have? And so there's been that conversation going on a very broad scale. And this is not like, just statistics. This is like effect on our daily lives in general, like people who aren't statisticians. And I talked to people recently, like I've had and Duke's had for years, like a pipeline of people to places like Google and computational industry and stuff, and they're now having this conversation, well, maybe we don't need statistics at all. Actually, it's about these deep learning algorithms. Well, the advances in those, the model that's been around for 30 years. Like the big advances are what? They're more data, and they're like engineering, Engineer the algorithms, engineer the system. Maybe we can get computers or chips that can not the old school computers, but they're designed, the architecture is designed to solve deep learning problems faster. If you could do that really fast, small, I could have a robot, and in its head I could have one of those computers, and it could be learning like a human, solving these deep learning algorithms as it moved around its environment. That's going to happen. Yeah, that's definitely going to happen, and it's been moving fast towards that. I'm optimistic about that. And the people I talked to, they were of the opinion that these deep learning algorithms, if you give it enough training data, it can do well at what humans are good at. Like I can look at an image and I know whether there's a cat in the image. Yeah, but maybe not so good at things humans aren't good at, and things we can't label as humans, and then feed it in as massive training data. Yeah. Anyway. So what I'm kind of interested in is sort of real science. And it's this old joke, really, that any field that feels it necessary to put science in the descriptor isn't. Like computer science or data science, or our department is named statistical science. And so what about like real science, like physics and biology and medicine and ecology and neuroscience? And what about those types of settings? Well, right now we're working on, we'd like to break open autism, understand the basic science of autism, get better treatments for autism. We're putting in like a $17 million grant that I should be working on instead of giving this talk on that. So can we solve those problems with machine learning and particularly deep learning? Okay. Also, there's this huge interest in precision or personalized medicine, like this dream of I can go and collect a huge amount of biomarkers from you, and I can predict how you're going to respond to different drug therapies. I can get a really good idea of what health conditions you're tend to develop, maybe whether you're going to develop even like depression or something, and I can really personalize or make precision the treatment for you, and I can even like warn you so you can like change your behavior to head off things that you might be apt to get. Okay, there's been a huge interest in that. We can really improve maybe diagnosis and treatment. But I would say, and this is really not widely known, even though it's sort of obvious, is that like sort of science, I'd say scientific data science and Google data science is totally different. Totally different. And so the people, like the huge number of people in this machine learning community, they have no clue about that for the most part. So the types of computational industry problems that have really been driving data science, and if you go to NIPS or something, it'll be dominated by that, are totally different than most problems in real science. And so in real science, what do we have? Well, we have few subjects relative to the data dimension. We don't have much training data. Like I work on cancer genomics and neuroscience, and you maybe have, if you're lucky, maybe 1,000 subjects in your study. You're doing whole genome scans, and now you want to see how that relates to their cancer risk, and how you should treat them for cancer, with the cancer treatment, with different types of chemotherapy or something. That's like totally not the deep learning problem. The deep learning problem is, I have really structured data, and there's something a human would be good at. I can look at the image and figure out what's in the image, and I have like 1 million labeled images. No, I have like super high dimensional data that I have no idea, as a human, I have no ability to look at and figure out what the pattern is, and I have few training data. And so we've had like almost no success in cracking open these problems, these precision medicine, personalized medicine problems. Those are like, we're so far behind this kind of creating devices for artificial intelligence or something like that, for pattern recognition. And so, and pretty much the deep learning, most machine learning isn't very relevant, really. You know? So what do? We need smart models that can deal with these types of problems. They're super needed. Because science is important. It has a huge impact on health and people's well-being and understanding, and we have few tools for that. And so I would hope that people moving forward would work more on these problems. And I find that more than that, they tend to naively apply machine learning tools inappropriately to these types of problems. Okay, so I'll just sort of wrap up. Everyone's tired of listening to me talk about brain connectomics, but in a more less statty way. Okay, so this gives like kind of an example of what I'm talking about, I think. So there's been amazing advances in imaging that are really allowing the collection of amazing data on, for example, brain structural connections. And here's an example down here of some of the data after pre-processing. And so this is an individual's brain. You're looking at this from the side, and like all of these little curves are fiber tracks that are like tightly bundled neurons that are controlling communication and processing in your brain. Okay, and then everyone's brain structural connectome is going to look similar to that, but there's going to be some differences. And those differences in how your brain's sort of wired might be having a big impact on behavior, yeah? And on how likely you are to be depressed, and how well you do in your linear algebra class, or whatever. And it's also dynamic, so you can measure your brain connectome, and then one of my collaborators, he would like have the people learn to juggle or take linear algebra or something, and then measure it again at the end, and there are noticeable changes. Certain regions have gotten larger, and things like that. Okay, so but how do we figure out the important aspects? Like we super can't use machine learning methods in general. We have this, that's our data for a given individual. We have that for lots of individuals. Actually, after pre-processing our data, what do we do with that? So there's some awesome data sets, like this Human Connectome project is pretty awesome. It's we have like say on the order of 1,000 individuals. You measure a lot of stuff on the people. Like the psychologists are involved, and they measure a lot of human traits and like your predisposition to violence and your anxiety and aggressiveness and IQ and lots of other variables. And we measure that, and then we give the people brain scans at the same time. And so here's like, this is just showing some of the shared structure in the brain from different angles and for different regions of the brain, and just kind of visualizing somebody's connectome. You can imagine that potentially this could have amazing impact diagnostically if you knew sort of what aspects were important in predicting some mental health condition, for example. Now we have no clue. You know, people, and it's an epidemic. Even like Duke undergraduates, I think 30–40% are on mental health medication. We have no idea what medication to give them. They go in, you give them some medication, you guess, and it takes a long time to kick in. And then you're like trying some other medication, and meanwhile it's just a disaster on these people's lives. And so that and like diagnosing mental health conditions, there's not one depression or one anxiety. And so if if we can get at the underlying wiring of these conditions, we could have a lot of really positive impact. But our data are kind of complicated. So how do we analyze these data? Just kind of wrap up pretty much. But we can take this might be your connectome, and so if you break it into regions of interest, like the connection between region of interest 1 and region of interest 2, these are all the little curves connecting that. And you can kind of simplify the data. We simplify it into a little array. It's like brain region by different features, measuring how strongly connected 2 pairs of your brain regions are. And then we can do a simple analysis to look at, what's unique about you relative to other people. And so we can estimate what are called like principal brain components. And so you have this brain object, and you turn it into different parts. Okay, and so maybe you have like more like one part than another part, so you kind of have a bigger score for the one part than another part, and so you get out these scores that are kind of summarizing your overall brain structure, and now you want to relate it to these other variables like creativity or IQ or other things, yeah? And we can do it just in a simple way, really. And we did that, I'm not going to go into the details, but you just do this simple tensor PCA kind of thing. And a lot, like extracting the brain scores of your brain structure, and then just doing a little analysis relating it to these different variables. These were quite significantly related. Like often up to, you could explain maybe 10% or even more, 15% of variation in, you give the individual language or vocal comprehension test, and you can explain maybe 10-50% of the variation in that score just by their brain structure components. Yeah, it's pretty amazing, because I think I work with a lot of psychologists, and if you can explain 10% of the variation, given how much noise there is in giving a test, that's pretty darn good. Working memory, language reading, decoding, locomotion, aggressive behavior, attention, anger, hostility, anger, physical aggression, etc. Some of this stuff was actually funded by the Army. I have an Army grant, and they were really excited about this because they'd like to be able to, a soldier comes in and you kind of scan their brain, and if they're more likely to be, have anger and physical aggression or something, they'd like to know about that and modify which kind of training program they would put in. So it's kind of fun. And this just kind of zooms in and shows some of the magnitude of the effect. And so this is just a distribution of some language, vocabulary, comprehension scores among individuals in the Human Brain Connectome project. And so if you say, well, these are low, these are high, and then you show this is just 2 of the brain components scores that we extracted, you can see that it separates people pretty well, surprisingly well, given how noisy everything is. And so that's it. So I was just kind of saying that machine learning and its deep instantiations are amazing, really amazing advances that are affecting all of our lives already. It's transforming our world instead of word. Our devices that we use all the time, etc. I think that things like driverless cars and stuff will certainly happen, and a lot of it will be using this technology. But let's keep in mind that these tools are good at certain things and they suck at other things, and we still need tools for those other things that are really, really important. So I'll just stop there.
Thank you, David. Well, if you have any interesting questions to follow up.
So interesting questions? If you have uninteresting questions, don't ask them. Everyone's probably tired.
So if deep learning you don't think is the way to address a lot of these scientific questions, what areas within statistics and machine learning do you think are most promising for future research?
That's a great question. I think what do we need? If you have really high dimensional data, there must be, in order to learn something, you're completely up the creek. Jim Berger was giving talks about this a long time about how you're up the creek, but you're completely up the creek unless there's some low-dimensional structure in the high-dimensional data. Like you can imagine the brain connectome. The data are huge, but maybe they're actually sort of low-dimensional. So maybe we can capture most of the variation or the important variation among people's brains by taking some low-dimensional, like brain components or something. And so if we can develop methods for really extracting low-dimensional, maybe geometric features underlying the data, and there are features that are particularly discriminative about some interesting outcome or phenotype, that's really important, A. And B, I think we really need in all of that accurate uncertainty quantification. Because a lot of the machine learning methods, like statisticians have kind of gotten away from characterizing uncertainty. You're like, oh, we do this optimization method because it's fast, and it spits out this result. Well, this result might be wrong, but you have no error bars on that result, and then you look at it and you overinterpret it, and then the scientific literature gets propagated with errors. And so we need like this kind of better dimensionality reduction, but with uncertainty quantification. And I would say exploiting more of the structure of the data. Like we need to put in a lot of prior information from mechanistic insight and propagate information across studies, and not just do the vanilla dimensionality reduction methods. Yeah.
So following up on that, one of the things that really like captured my attention recently is like the intersection of like deep learning with like the Bayesian inference, like the Bayesian deep learning. Do you think that, because that is going to give you like some more measure of that uncertainty there, do you think that's a fruitful endeavor, that intersection? Or
yeah, I mean, I think that marrying, like Larry Karen at Duke is one of the leaders in that area. Most of the people currently who do that intersection, they're not actually, I would say, significantly improving on vanilla deep learning, because maybe they use some variational Bayes algorithm and they're not properly characterizing uncertainty, and they're not putting in real prior information, and they're not getting interpretable inferences. And so often in scientific things you want to know something about what the structure is. And so, but to the extent that you can do that, maybe we can learn from the fact that neural networks are really actually pretty good, and they beat like the black box, they beat in Bayesian hypermetrics in terms of prediction. But can we put in something that's get something more interpretable out of it with uncertainty quantification, putting in more information, because there's a lot of mechanistic information from mechanistic modeling, can we marry that with deep learning? The directions like that are really promising. That was a great question.
Yeah, so I guess I have several chats with Jeff Wu at Georgia Tech, and he always thought, okay, instead of science, we should do more like engineering. So rather than statistical science, we really to be statistical engineering. And then I just learned a few weeks ago, actually, the Berkeley statistics department moving to the School of Engineering. And then I'm not sure what do you think about that.
Yeah, I mean, I don't mind whether you call it. I mean, I think that probably it would be more realistic to call much of what's done in data science data engineering. That's true. But I think whether you call it data science or data engineering, I don't care that much. Yeah, I don't know if I have any intelligent thought about that. The one issue, though, is that it is true that there's this sort of statisticians, and if we're not more adaptive, there's these kind of engineers who are pretty smart, and they can come in to these problems, and maybe there's a lot of data science money, or even a lot of money in an applied domain like neuroscience or something, and they can take that money and they can do stuff with it. And if they're more fast about giving answers from the data, some of it is probably pretty high quality, but maybe without the statistical understanding of the uncertainty quantification. Then they're going to be beating us out. And statistics is going to be this kind of sad sister field of grouchy people who complain about the engineering methods that everyone's using. So I think that is a really big issue. Yeah. And so all of us should be having an eye across these fields. I don't know. I have an affiliation in electrical engineering and math. And I pay a lot of attention to what these other people are doing, and there's really high quality people at Duke. They don't know much statistics, but they're doing a lot of statistics type things, data analysis type things, but usually without that kind of thing that statistics adds, which is so important in these scientific applications.
Comment that you mentioned personalized medicine, and all this, the emphasis is so much on the models. People often talk, well, maybe deep learning might perform better than more simple models, but another important question is, well, what criteria we actually use to determine success, right? So I think there is a big component for the statistical decision theory to be incorporated. So that's one part. And another part, for example, with all this personalized medicine, it's also a big part of it is design, how we design these studies. And that's also a big statistical component. So it's not only about the models, but how we quantify success of those models. How do we quantify the uncertainty? So the combination of statistical theory and design is also important.
Yeah, I mean, those are really fantastic points, super good points. I mean, the two being that, how do we measure success? And so most of us have gone to this thing where we do cross-validation. We hold out some data, we build our model or statistical approach, and then we see how well we do, like outside of the data that we fit the model on, this kind of cross-validation. And that can be really misleading, you know. So some machine learning method might do great for that, but then I'm often really interested in, say, variable selection, or what's the structure related to this health phenotype. And you can do super bad with that and still have good generalization error. And so how do you assess how well you're doing? I've been struggling with that lately, yeah. It's important. Two, the whole design problems are super important. And we don't use that. We don't have enough people in the discipline working on that. We don't work on it enough. Yeah, it can have an enormous effect. Like if we use an adaptive design in a medical application instead of kind of a usual approach that people tend to use, then we can really improve the efficiency. So I think there's a need for a lot of that, or even design-based thinking in dealing with big, complicated data sets. Yeah, great points.
We have no more questions. Then we should thank David one more time.